So let's begin the second morning session with a talk by Jules LAMERS from Daisy Hamburg / Glasgow, and he's going to talk about a solvable non-unitary fermionic long-range model with super extended fancy symmetry.
All right, thanks. So thanks to Samuel and also Rodrigo for organizing this very nice meeting. I'm really enjoying I understand that there's sort of an underlying hidden theme here, but now somehow the talks are a bit eclectic, and I think it's very nice actually. So we get to see lots of different facets of integrability, and we have this sort of common feature, but somehow lots of different roots from there. So here I'm sort of going to talk about work which is secretly related to things that Martin was talking about, but I will not really go there at all. And then it continues a bit with things like what Balázs was talking about. So they're fermionic models that are that have long-range interactions, because when I talk, it's always about stuff with long-range interactions, and they have lots of symmetries indeed. So please ask questions when you have them and interrupt. Okay, so motivation. Let me try to go here so that I can see the slides too. So okay, so let's start with something very basic. We take the Heisenberg spin chain. Let's take XXZ. So here's on a circle like this with n spin 1/2 sides, and so we have our Pauli X, Pauli Y, and Pauli Z with this delta anisotropy here. And there's a way to rewrite this Hamiltonian here using these special combinations of Pauli matrices that are temporally leap generators. Namely, you define basically what I have here, but now I prefer to call delta Q plus Q inverse over 2. And then I add and subtract a term which cancels. If you add them here in this sum, you see that this one from EI will cancel this one from EI plus 1 and so on. So it kind of really doesn't matter in the sum. And then for the periodic boundary conditions here, I have to take one more and I have to kind of periodically move it around the chain to make sure that I really get my periodic spin chain here. And these EIs, they're very nice. They obey these relations. We saw them in Marius's talk as well. So they're sort of projectors up to normalization. So they square to themselves. And they have this funny relation that graphically has a nice interpretation. Algebraically, the temporally Lieb algebra is interesting because it is the centralizer of quantum SL2. So this space here has a representation of quantum SL2, and these EIs, they precisely commute with quantum SL2. So they commute with quantum SL2, and anything that commutes with the quantum SL2 action on here can be built from EIs. But if you look at the Heisenberg spin chain, you see that here, besides the EIs, there's also these normal permutation operators. They're not built from temporally leap, so they don't commute with UQSL2, and that's why XXZ is only SZ invariant, but not UQSL2 invariant. But there are modifications of this Hamiltonian where you change a little bit these boundary conditions here, so that you do get quantum SL2 invariant. So just, for your general background, one thing to do is you can just remove this here. So you take this stuff here. So then all these extra terms, they cancel on the sort of in the bulk of the system, but on the boundary we have an SZ1 left and an SZN left with opposite signs. So this is a special case of an open XXZ spin chain, and it has UQSL2 symmetry. Another thing that you could do is you can replace these permutations by something called Hecke algebra generators, which is Q minus this EI here. If you send Q to 1, it would just go back to the permutation, but this is built from temporally leap, so it still commutes with UQSL2. Anyway, this is just for the background. I want to say that you know the XXZ spin chain secretly, you can rewrite it in terms of this temporally leap algebra, and this allows you to kind of, even though you Q deform or you make it anisotropic, you can formally keep this spin symmetry very much like the SU2 case that you have for normal XXX. But you need very special boundary conditions. And physically, these boundary conditions might make your Hamiltonian non-Hermitian. So this is kind of will be in some sense the origin of the word non-unitary in the title. Now, one special case of this XXZ Hamiltonian is you can take delta as 0, or in terms of this Q here, you take Q as I to cancel this part here, and then we get free fermions. So Balázs talked about this. We can do Jordan-Wigner, etc., and you can describe the spectrum explicitly. Of course, again, it depends sensitively on the boundary conditions, how this works, and it might be simpler or more complicated depending on that. Okay, so now I want to go long range. And before doing so, in really the setting that I want to talk about, let me just kind of briefly mention this spin chain, which is one of my favorite models. It's called the Haldane-Shastri spin chain. It is still a model of n spin 1/2 sites, but now they interact at longer distances, these spins. Physically, of course, you want the interactions to be a bit weaker if the spins are further apart. So there's this potential 1 over sine squared here that suppresses interactions a bit as you go further and further apart. And geometrically, if you think of this as being the unit circle in the complex plane, or just the unit circle, then this is 1 over the chord distance squared, this potential. So it's sort of a nice geometric potential. And this model was found by Haldane and Shastri independently in the late 80s, and it's a toy model for the fractional quantum Hall effect. So even though it is just a lattice model, finite dimensional, it exhibits certain fractional statistics and other kind of nice features that appear in the fractional quantum Hall effect. And it has very close connections to CFT. So you can think of this model as sort of a very precise discretization of West-Domino-Witte level 1. Anyway, so this model was found to have, was physically motivated, but then was found to have a lot of very cool kind of more mathematical properties. So its many special properties include that the spectrum can be written down exactly. So this is kind of a nice exercise. If you've never done this before, if you've never seen it, take this Hamiltonian, put it in Mathematica, numerically diagonalize, look at the eigenvalues, do this for the first, like up to length 10, and you can essentially, if you stare at it for about a while, you can predict what the spectrum is for any system size. Because the spectrum, the eigenvalues, up to some overall factor, are just integers. Not all integers occur, and there's this kind of a simple statistical rule that says which integers occur. So it's really very, very, so you don't need to do beta ansatz, there are no beta ansatz equations, it's much more kind of solvable than the Heisenberg spin chain in this sense. And another related kind of very special property is that it's extremely highly degenerate. So this model has a lot of spin symmetry. So it's not just SU2 symmetric like Heisenberg XXX would be, but actually there's many, many more symmetries. Namely, there's a representation of the Youngian. It's not the one for Heisenberg, but a different one, which commutes with this Hamiltonian. So it means that you can construct an ABCD operator and they commute with this Hamiltonian. So you can't use algebraic beta ansatz, but instead you get lots of symmetries. So you can have lots of descendants of a single highest weight vector to start with. So, okay, so this model is very cool. It has explicit spectrum, very simple, and lots of degeneracies. Now, this was the kind of XXX level, so it's natural to wonder if you can extend this to the XXZ level. And this can be done. So it was sort of algebraically set up by work by Bernard Godin, Haldane, Pasquier in the early 90s. And then Ugloff found, they kind of said, if you do this, then you should be able to find the spin chain, but they didn't manage to do all the computations to really find the spin chain. Then Ugloff actually did those computations and managed to get the result. And but his result was extremely complicated. For some reasons I was interested in it. I found his paper, which somehow went unnoticed, so nobody really found it or knew about it. And I managed to write the Hamiltonian in a kind of a nicer form. So the interactions look a bit like this, where very briefly, this is an R-check matrix of UQ SL2 with spectral parameters. And what you do is, rather than here, you have essentially a permutation of spin I and spin J, or 1 minus a permutation. So here you use R-check matrices instead of normal permutations to move one of the spins next to the other. Then you interact with temporally leap, which is the usual XXZ nearest neighbor interaction, and then you move it back again with these R-check matrices. And it turns out that these interactions are more complicated, they're less physical, they have multi-spin kind of stuff and all sorts of things like that, but they allow you to precisely keep all the nice integrable properties of this model here. So the Youngian gets replaced by a quantum loop algebra that commutes with this Hamiltonian. I don't want to really write down the Hamiltonian, but it has essentially this form with the Q-deformed potential that is simple, and these interactions instead of the permutations there. And okay, so the price we pay is more complicated interactions, but we keep integrability and we get a sort of a U1 only symmetric version of the this Haldane-Shastri spin chain. And again, because we want to keep the nice spin symmetries, we need to get certain special quasi-periodic boundary conditions, which will make our model typically non-Hermitian, depending on the value of Q. So for Q real, it's still Hermitian, but for Q on the unit circle, it's not quite Hermitian. So okay, natural question. We have this model here. Everything works very nicely for generic Q. So can we take Q a root of unity? And let's take the simplest case and just take Q equal to I So we expect free fermions just by analogy with Heisenberg's spin chain. Now, since here, actually at the general Q level, we know everything very explicitly, we can just look at the spectrum and we can set Q as I, and we know what the spectrum will look like of this Q-deformed Haldane-Shastry spin chain at this to-be-expected free fermion point. And we see indeed that it's extremely simple. There are really lots and lots of degeneracies, so even more than for Haldane-Shastry. And well, we can see these type of things. But since the interactions here are rather complicated, it's actually not so easy to write down explicitly what the Hamiltonian with this very simple kind of free fermion type spectrum looks like. So this was quite a lot of work, but we managed to do this. And my goal today is to tell you about what the result is in two ways. First, the kind of the complicated thing that you would get by specializing this model to Q as I. And then I will kind of forget about almost all of it and just do a kind of a free fermion in disguise type of construction of these Hamiltonians. So, okay, so here's the overview. So we have this Q-deformed Haldane-Shastry spin chain, which we will call the parent model. And it has a translation operator, but it's a kind of a modified translation operator because we don't quite have periodic boundary conditions, because we want to keep this extra spin symmetry. And then, rather than just one Hamiltonian, the model becomes, well, you saw it in the picture here, it becomes kind of chiral. This interaction is not left-right symmetric. So there exists a Hamiltonian with these type of interactions where the right particle moves to the left, and there's another Hamiltonian which is kind of the left-right flipped. And they're different, but they commute with each other. So that's what I mean by a left Hamiltonian, the right Hamiltonian, and they commute, so I can also take their kind of average. And if I take Q to 1, then they all become the same, just this Haldane-Shastry spin chain that we had here. And then in principle, there's a whole family of higher Hamiltonians, because the model is integrable. So what we will do, so for Haldane-Shastry, you send Q to 1 and you get back the normal translation, the normal Haldane-Shastry Hamiltonian, and so on. So today what we're going to do is we're going to set Q to I, then we get some sort of weird translation operator, which is not periodic, but it's suitable for our case. We will get some kind of chiral Hamiltonian, and we will see that this is a free fermionic Hamiltonian. And this kind of average here is really kind of still an interacting type of Hamiltonian. It has quartic interactions, as we will see, that implement some sort of statistical interaction rule. So this is one result, kind of high level, that I will explain in more detail. The other thing is that, okay, so I told you that Haldane-Shastry has not just SU2 or GL2 symmetry, but it has really a Youngian worth of symmetries. So in the Q-deformed case, we have quantum GL2 or the quantum loop algebra worth of symmetries. And if we set Q to I, then we get this super Lie algebra GL11, or a kind of a little bit of an extension there, which acts by symmetries. And we know in general there should be some sort of affine version of it that acts by symmetries. We can see it in the spectrum. But this is a part that we don't actually quite know yet. So we don't, maybe Azad knows what the result here should be, but we don't know yet. But certainly our model has more symmetries than just this GL11. But I'll talk about it. And of course, our model has an explicit spectrum. It is non-unitary, but there is a version of PT symmetry, which guarantees that the spectrum is real. And it has very, very high degeneracies. So this is really essentially the takeaway message of the talk. Sorry?
Could you go one slide back?
Yeah, absolutely.
So in this picture, you have moving back, the blue diagram.
This one here, yeah.
Because here you have now a choice over and under.
No, but this is our check matrix. So yeah, so it's unitary. So it carries spectral parameters and doesn't matter. No, so there's no choices there. Okay, so this is the plan for the talk, really. So to say mostly more about the commuting Hamiltonians and a little bit more about this extended symmetry and give an example of what the spectrum looks like. Okay, so first I want to start with these fermions. So normally what you would do if you go at the free fermion point for xxz is you do this Jordan-Wigner transformation, which introduces kind of lowering and raising operators, but with a tail of q to the sigma z to the left of it, something like this. Well, not q, well, but plus or minus I, 1. So here we have to modify. So then we get these Jordan-Wigner fermions, which are just canonical fermions. I denote them by Cj and Cj dagger. And we don't really want them. So following actually Azad and Hubert Saleur and others, it's actually useful to rescale them a little bit by factors of I. and so that we define things that we call F and F plus. This is not a dagger anymore because it is not, these two are not Hermitian conjugate, but they're still, they play the role of the C and the C dagger, and these extra i's are just useful to avoid i's from showing up everywhere else. And then the canonical anti-commutation relations are modified a little bit, so we get this alternating sign there, where normally you would just have a 1. So this is very nice, these operators, because then you can form kind of these, well, quadratic combinations of these F and F pluses, and you can check that the resulting EI actually obeys the temporal leap relation at the value Q is I, so the free fermion temporal leap algebra. So in particular, they square to 0. And from these temporal leap generators, we can already write down the first thing, which is the following. This is our modified translation operator, or quasi-translation operator. And what we just have is some linear combination of these temporal leap generators. More precisely, it's quite well known that if you take a temporal leap generator and you take a suitable linear combination of it and the identity, then you get the R-check matrix of UQ SL2. So here, we just use the R-check matrix in sites 1, 2, which is this little picture, and then we multiply all the R-check matrices all the way to n minus 1 and n. So you kind of do again an R-check modified version of a translation operator, and this turns out to be the right translation operator in our case. And these combinations here are tangents because we're at Q is I, so the coefficients in the R-check matrix look a little bit different from what you're maybe used to. And okay, so this thing here, if you would have general R-check matrices and you send Q to 1, then they become permutations, so it's the usual translation operator. But for Q is I, it's different. It's not quite, it's certainly not periodic in the standard sense, but it has the property that the nth power is 1. So formally, we have a model that looks periodic. So this quasi-translation really takes over the role of translation operators. Okay, so this is the kind of, this says a little bit about the type of boundary conditions that we have. So it's kind of formally periodic, but not really normally periodic. It's a bit weird. A bit more like this kind of topological, kind of somehow twisted thing. Okay, so now from this point of view, I want to continue. So we need one more ingredient, not just these temporal leap generators, but we need nested commutators of temporal leap generators. So let me introduce a notation that E with the bracket I plus 1 is just our old temporal leap generator. And then I define E of, well, it's supposed to kind of suggest a commutator, I to J, is, well, recursively defined as a commutator of temporal leaps here. So you take a kind of a string of adjacent temporal leaps and you take a commutator nested in one way or in the other way by a Jacobi identity. You can relate them. So these are special combinations of temporal leap or of these fermions. And then our chiral Hamiltonian that I mentioned before is just a linear combination of precisely these nested temporal leap generators with explicit coefficients that are some explicit functions of these kind of tangents appear in there. So it's kind of, it looks a bit like a two-side Hamiltonian, like a long-range two-side thing, like Haldane-Shastri, but with different coefficients, and now these nested commutators of temporal leaps sitting there.
But if we compare with what Balázs told us, for him coefficients were more or less arbitrary, and there was
right. No. So we're looking at a very special case because we want to have all these properties like lots of extended symmetry, etc., etc. So we have a very specific model here. But I will show you a little bit how it relates to such a type of formula. Yeah, the algebra looks similar. That's right. So then we have this other Hamiltonian, which is kind of the Hamiltonian, and it is a little bit similar, but instead of just a nested commutator of temporal leaps, we take one anti-commutator of nested commutators of temporal leaps. Again, with explicit coefficients that I don't want to write down, and some prefactor. So these are the Hamiltonians that you get by tedious computations from the general Q-deformed model by specializing to Q as I and doing lots of stuff to try to kind of really write something that looks a bit more palatable. It still looks a bit abstract, but there's a very nice property of these temporal leap things. So what you can check using these relations is that the nested commutators of temporal leaps are actually still just quadratic in fermions, now just with fermion I plus 1, and then j minus 1j, and the other way around. So it really looks kind of a bit similar to what you have here, but now instead of just I and I, you have I and j. So it's still a quadratic combination here. So we see that this Hamiltonian really is explicitly quadratic in these fermions. So in that sense, it is a free fermionic model. Whereas here we have one anti-commutator, and then we actually get quartic terms. And so here we have an interacting model, which has a quadratic kinetic part plus a quartic interaction for fermions. So this is what our model looks like explicitly. It's a little bit like in this Q-deformed Haldane-Schuss 3-spin chain. The spectrum is kind of guaranteed to be very nice by construction, but the Hamiltonian is, you know, it's not quite fantastic. It is a little bit complicated, but this is the way it is. So now, let me say a little bit about these lots of symmetries that the spectrum has. So we have these same fermions. So so you can define a set of generators which gives this GL1/1 super Lie algebra representation. So this was again done by Azad and collaborators. So one thing is, okay, this is just a central charge, which for us is -1. So it's not so interesting. It's an even degree 0 thing in terms of fermions. Then at degree 1, so we have two odd generators, which are just the sum of all the Fs or the sum of all the F pluses. And they anti-commute to this central charge. By the way, I have to stress that we take, I kind of skipped over this, sorry. I should go back here. So for us, at Q is I, N is even and N is odd behaves radically different. And you can sort of understand this if you know a little bit about Q-deformed stuff, because you get quantum integers appearing. And if you set Q is I, then all even quantum integers are 0 and all odd quantum integers are 1. So you see that somehow even and odd has a very different kind of role. And in fact, in our what we see is that our Hamiltonians have, for n is even, they have poles, because our check matrix has a pole, and also the potential has a pole at when the particles are opposite. So this is very different and kind of complicated. So I want to focus on odd number of sites. That's actually very important. I should have mentioned it. And this is the reason why this central charge, which is just a sum of plus, like an alternating sum here, is always -1 for us. Okay, so then we have these two fermionic generators here that anti-commute to the central charge, and they square to 0. And then we have something which is the number operator, but I kind of think of it in a spin chain language, so I call it M, kind of like a Magnon number, but it's really the fermion number for us, which is just the local number operator, and then with this alternating sign, because we made this little modification to our fermions. And then you can check that this number operator commutes, because it's an even operator, so bosonic operator. It commutes with F and F plus to just -F and +F plus. So it's a good number operator. And so these all commute with our Hamiltonians. So we have GL11 symmetry. But actually there's a little bit more. So if you're careful and you take UQ GL2 and you take Q as I, then you do not just get this, but you can also get an extra set of generators which are quadratic in fermions or in the creation and the ionization operators of the fermions. And they're also part of a slightly bigger algebra that is sometimes called curly A subscript 1, 1. And right, so these are all symmetries of our model. But in fact, we have more, because as I mentioned, we have really, before the parent model for general Q is known to have this quantum loop algebra worth of symmetries. So we will get some sort of affine version of this GL11, and we suspect it might be a Youngian. We don't quite know yet. We have a general formula, but it's again hard to kind of make it concrete in our case. So we're okay. Yeah. So we don't quite know what this is yet, but certainly they all commute with our Hamiltonians, and I will demonstrate a little bit later with an example that we can see them in very high degeneracies in the spectrum. So they do have a practically they're already visible in our model. Okay. So now this was the version 1 of the model, which is kind of explicit but not super elegant. So now we're going to go a bit more elegant, and the key here is this quasi-translation operator, because this is really the right way of kind of moving stuff around. So what we're now going to do is we're going to take these fermions, but we're going to actually throw almost all of them away except for the first fermion. So we start on the left of the lattice, and there we create or annihilate our fermions, and then we translate them around using our quasi-translation operator. And pictorially, you can check that if you take these pictures and you kind of do the computation and use the braid relations and so on, then these generators have the following form. You take the jth particle, you move it to the left, then you create or annihilate, and then you move it back to side j. So if you do it like this, then, well, since the quasi-translation operator, its nth power is 1, these fermions are kind of periodic in this j formally, in the sense that if you shift j by n, then well, you don't see it. So now we have something that looks formally periodic, and quite with a bit of work, you can compute the anti-commutators here, and you see that there's a non-trivial relation only for phi I and phi dagger or phi plus j, but it's not quite well for any I and j. So it's kind of not just canonical commutation relations, but there's really some sort of non-trivial function here, but importantly, it only depends on the distance between the two fermions. So here we have something that's formally periodic and something that depends on the distance. So we're in a good position to Fourier transform. So let's take these kind of more complicated dressed fermions and Fourier transform them, and then we rescale a little bit by some simple coefficients, factors of I, and then remarkably, we obtain really canonical fermionic mode operators. So even though we have complicated translation operators and we have kind of everything looks a little bit complicated, we end up with just canonical fermionic modes operators. And they have the right properties that if you conjugate them by the translation operator, then you get out a factor of what is kind of the momentum. But this is, I mean, it's kind of like the topological momentum for this kind of funny version of the translation operator. So now these are the right fermions to rewrite the everything in. How much time do I have left, actually?
For 3 more slides.
Okay, very good. So we take our Fourier transformed dressed fermionic operators that are canonical. Then the first observation is that if we take n is 0, so we don't have all these plane waves here, and we just get a sum over these translated fermions, and we can check that this is actually just the sum of the fermions, because the translations are here they don't contribute. So we just get the one step, like the creation annihilation operator of this GL1/1. So the zero modes of our dressed fermions are in fact part of the symmetries of the model explicitly. So this is kind of nice, and they commute with the conserved charges. So in particular, the Hamiltonian and so on, they will not feature these zero modes in the Hamiltonian because they commute with them. Whereas if you take all the other fermionic modes, creation and annihilation operators, then they're linear combinations of these kind of two-side fermions. So the old fermions, not the fancy fermions, at side 1 plus 2 and so on, all the way to n minus 1 plus n. So there are n non-zero values of the, big N minus 1 non-zero values of the little n here, and there are big N minus 1 combinations of two-side fermions like this. So that's a nice match. It's a non-trivial linear combination, but we can compute it. Okay, so everything will be built, the Hamiltonians will be built from these non-trivial fermionic modes. And the result is actually really quite nice. So our chiral Hamiltonian really becomes just quadratic in terms of these fermionic modes with an explicit function here, which is our chiral dispersion relation, and it's very nice. It is just a linear branch, which if you think about this momentum, it's kind of, so this is the mode number n, which is big N periodic, and this is the energy. So here, if I'm big N periodic, you can kind of think of this really as the continuation of a single linear branch. So it's a relativistic chiral dispersion relation, but on the lattice, right? It's just a totally discrete model. So I think this qualifies as kind of a very kind of complicated version of a free fermion model in disguise, this Hamiltonian here.
And your epsilons are any real numbers, or?
These epsilons, they're just these values. So epsilon n is either small n or big N minus small n, depending on whether you're even or odd. So we have these two branches, and you alternate between the two branches. So it's real and very simple. Just linear. So yeah, extremely simple. I think you can't get much more simple than this, really. Then this full Hamiltonian, again, has a quadratic part with a very simple dispersion relation. So this here is actually obtained by taking the absolute value of this here. So we have two branches, but now one goes down and one goes up. We again alternate between them depending on whether the mode number is even or odd. And well, if you would allow yourself a little translation and you kind of center yourself here, you see that this is a massless relativistic dispersion relation on the lattice. We really just have two linear branches. So I think this is kind of cool. Now we get a model with this massless relativistic type of dispersions, even though we're just a lattice discrete model. And I think this is the closest that you can get to such a, I mean, you need to kind of, if you have two branches, then you better kind of alternate to them. And if you increase n, the only thing is that you just have more and more points on this thing. So this is very nice. It seems very well suited for taking n to infinity, at least at this level. Okay, so that is the quadratic part, but there is more, because now we have a quartic part in terms of the quartic fermions with some function here. So we haven't quite been able to kind of properly prove this, but with lots of numerical evidence and so on, we can see that this V tilde here, so let's say Fourier transformed potential part here, is almost always 0, and otherwise it is just plus or minus 4. And the non-zero cases occur when this little n and n prime is odd and equal to the n double prime plus n triple prime. So there's a very simple selection rule that says that this potential here, so if you have this, if you think of this in terms of long range hopping, you need to kind of conserve essentially. So this is kind of a stronger version of momentum conservation and chiral energy conservation. It's a little bit stronger because we also require this sum to be odd. And right, so this Hamiltonian is interacting, but very simple and quite cool, I think. So let me illustrate a bit more what this looks like by going to an example. So this is just a repetition of what we've just seen. So the obvious thing that you do is you construct a fermionic Fock basis. So you start with something that's annihilated by all the psi tildes, and then you create fermions with the psi tilde pluses, and we call this our Fock basis. Then this is diagonal, so it just has the sum, which is the sum of these chiral energies for the different modes, and the momentum is just 2 pi over the system size times the sum of all the mode numbers. So again, very nice and simple. But this Hamiltonian is not quite diagonal because there is this interacting part. So let me just illustrate how this works, and this is again actually very nice. So this simple potential has some very nice consequences. So I just want to look at this for the case of 5 sides. Where you see all the features, but I can still draw this. So here the picture is, this is all the eigenstates of the model. So the full basis, not just the Fock basis, but the full basis. And the picture is as follows. So here on the vertical axis, I record the fermion number. So here there are no fermions, here it's maximally filled, and here we have all the in-between states. If I write here empty, this is just a short, so I write the Fock basis, but I omit the cats for brevity. So this is the Fock vacuum. It's an eigenstate with energy 0, momentum 0, etc. Now remember, we have our GL11 creation and annihilation operators, and we have this kind of one-step operator and the two-step operators, because we had this curly A11. We had a little bit more than just GL11. So I will draw the GL11 generators as kind of going, well, in blue. So they create or annihilate one fermion. So if I take the fermionic vacuum, I can create a descendant of it, which is by adding the 0, acting by the 0 mode. So that's this state. This is the Fock basis with, so here I allow for the n to be 0. So that's that one. Or I can act on it with this F2, and I would get some other state. I'll get back to this in a moment. Now at one fermion, so I have the 0 mode, or otherwise I have all my other modes. They're also eigenstates of everything, because we conserve particle number. Now again, I can act by my one-step GL11 generator, and I add the 0 mode, so that's all these lines here. Or I can act in 2 steps, and so on. So now the interesting thing that happens is what happens at 2 fermions. There we really start to see the influence of this potential. And it works as follows. So let's first start here. So these states have, well, we can check here, if we add 1 plus 3, then we have an even number, so the potential is 0. So in this case, the potential does not contribute at all, and these states are kind of protected by the selection rules in some sense, so they're just eigenstates of the Hamiltonian. So some of the Fock states, even for multiple fermions, are eigenstates of the Hamiltonian because of these quite strong selection rules. If I added a 0, nothing interesting happens, so I'm going to disregard those. So then there are 2 other cases. One is the case like this. Let's take the right one. These 2 are related by parity. So let me focus on the part here. So if I have 2 adjacent fermionic modes, then what happens is the potential is not quite 0. I add 1 and 2. I get 3. It's odd. So it's in principle allowed. And we can check that indeed this potential is non-zero, but it's kind of diagonal. So this part contributes to the energy, but the Fock state is still an eigenstate. So this 1, 2 is an eigenstate, but there's the funny thing that if you take the dispersion of the first fermionic mode and the dispersion of the second one, and then add the contribution of the potential, then we actually get the energy of this third mode. So what happens kind of is that the first and second modes are squeezed together into the number 3. So you do 1 plus 2 is equal to 3, and it is in fact, so this is going to be an affine descendant with this extra symmetry of our one fermion state that we have here, and similarly here. So this is kind of here, we see at the level of the spectrum that indeed our model has this extra symmetry on top of this AGL11 thing. So we believe that this should be some sort of kind of Youngian GL11 maybe generator or something like that. Now, so summary, some states are protected by the selection rules. In other cases, the potential contributes, but only diagonally, so we're still eigenstates. And then there are cases in which it contributes and you get some mixing between states. So here, there would be the Fock state 1, 4, and it is again mixed through the rules of the potential that I didn't give in full detail, determining this sign. So 1, 4 is again related to 2, 3 by this sort of squeezing. You take the numbers 1 and 4, and you move them one closer to each other, so you get 2 and 3. So the Fock states 1 and 4 and 2 and 3 are mixed by this Hamiltonian. And so you can try to diagonalize them. And this will give states that I will denote by 2, 3 prime and 1, 4 prime that are actual eigenstates. So these are non-trivial linear combinations of the Fock basis. And then what we can check is that one of the two actually corresponds to a kind of a double descendant of the Fock vacuum, which is kind of nice because, you know, this 2, 3 again is, if you would push them together, they're already adjacent. So you kind of squeeze them together and you would get 5, which modulo 5 is 0. So it kind of, there's a kind of a funny combinatorics going on here. And then there's a second state, which is really linearly independent that we get from here. That's a non-trivial fermionic state. Okay, so this is a detailed example of what the spectrum looks like, but it illustrates how we have our GL11 symmetry, how we have a little bit more than that, and how you can also see affine symmetries. In general, in the fermionic language, what we do not yet know is what the affine symmetries look like concretely, or what algebra they precisely are. And we do not precisely know, I mean, from the parent model, we have a construction of the full like all eigenstates. But again, it's not so easy to specialize Q equals to I. You get some maybe zeros or infinities, you might have to regularize, or you get Jordan blocks, all sorts of things can happen. And so it's not completely obvious. So what we're trying to do is get really a fermionic construction of the full eigenbasis. And so what I illustrate here is that we know in general up to 2 fermions, we know exactly how it works, but we haven't quite worked out the combinatorics in general just from the fermionic language beyond 2 fermions. Okay, so this is really our model that we have. So it's kind of a very complicated version of free fermions in disguise for the chiral Hamiltonian and free fermions with some statistical interaction that models some sort of a selection rule. So actually, maybe that's the last thing that I should mention. So okay, so let's look at those Fock states that are actual eigenstates of the Hamiltonian. So we have empty and we have all of these. They're a bit boring. So those two, so the things that are protected by the selection rules are precisely those where there's at least these mode numbers are not adjacent. So they differ by at least 1. And this is precisely the selection rule that we knew from Haldane-Shastri. I mentioned that there was a very simple rule that says which energies occur and do not occur. Well, it's precisely the rule that you're not allowed to pick adjacent numbers. And you see that whenever we picked adjacent numbers, actually secretly it was already a descendant for the symmetry rather than highest weight, or it was a descendant slash a highest weight state that we had to get by some non-trivial diagonalization of a 2x2 block here. So it's kind of cool. We really see the structure of Haldane-Shastri appearing just from the fermionic language. Now, the very last thing that I want to conclude with, which I think is good and appropriate because those of you who have seen talks of me before have always seen this slide, so I think I should advertise this slide again. So what I've done so far is I've talked a little bit about the Heisenberg XXX model and the XXZ model. And I've talked about the Haldane-Shastri spin chain and this Q-deformed Haldane-Shastri spin chain. And today I talked about how you can set Q equals to I and get some non-unitary long-range fermionic model with lots of symmetry by setting Q as I here. But now we know that there is actually, well, there exists some spin chain that interpolates from Heisenberg to Haldane-Shastri while remaining integrable in between. This is called the Inozemtsev spin chain. It's a very complicated spin chain. It has an elliptic pair potentials related to elliptic Calogeros-Sutherland type of models. There's some sort of beta ansatz construction for the spectrum, but it's very complicated because everything is elliptic. But the cool thing is that it is integrable and it is exactly solvable. So it really allows you to trace what happens with the beta ansatz from Heisenberg all the way to Haldane-Shastri with all these extra degeneracies using some sort of beta ansatz, etc. So it's an integrable interpolation between the short range and the truly long range setting. And one thing that recently with the collaborator Rob Klabbers, we've managed is to Q-deform this Inozemtsev spin chain. So now we also have intermediate range thing that interpolates between this Q-deformed Haldane-Shastri and, well, okay, it's sort of a twisted dynamical, so a slightly decorated version of the Heisenberg XXZ spin chain. Because again, we can't quite tolerate periodic boundaries at the Q-deformed level, so we need some sort of slightly different boundary conditions. And so an obvious question for the future, besides those that I posed of identifying the extended symmetry and really understanding the spectrum just in fermionic language, is one could go elliptic and really seize to get a sort of an intermediate range free fermionic model that's non-unitary. And I think, you know, because this dispersion relation was well adapted to take n to infinity, and it kind of seems to have a chance of connecting nicely with certain CFTs and so on. So that's the other thing. We want to try to take n to infinity and see if we can connect this to CFTs. Maybe symplectic fermions might appear because we have lots of symmetries here or not. So this is really, we feel that there's a lot of possibilities for the future. And with that, thank you very much.
Any questions to the speaker? Also questions.
Could you comment more on the quantum loop symmetry? I mean, you mentioned that for Q-generic you have quantum loop symmetry.
Right.
I mean,
okay, so okay, for generic...
Is it a full symmetry of the Hamiltonian, or full non-abelian symmetry, or...? Yes,
so for generic Q... Okay, now I'm going to go very fast and relate a tiny bit to what Martin... So you have this... So, okay. So in terms of quantum toroidal algebras, which I know you know, I think. So if you look at this picture here, so for the Heisenberg spin chain, we normally have the vertical subalgebra of the quantum toroidal algebra there. That is the monodromy matrix that we use here. The symmetries of Haldane-Shastri, they're the horizontal subalgebra of quantum toroidal algebra. So in terms of representation theory, you take the affine Hecke algebra with Cherednik Y operators, and you use this Drinfeld functor. You get some sort of non-trivial representation of the quantum loop algebra on your spin chain space. That is where this symmetry comes from, and this is really the full symmetry of the Hamiltonian. So it fully controls all the degeneracies for generic Q.
How do you prove it? Empirically, or you just look at...
Well, I mean, we can do the counting. So we can construct explicitly in terms of highest weight. So the quantum loop. So we can construct this highest weight. The quantum loop algebra. We can construct the highest weight. So the loop highest weight vectors for our quantum loop algebra action. We can compute their Drinfeld polynomials, so we know the dimensions of all these highest weight algebras. We know their eigenvalues, so we know that they're all different, etc. And we can check that it really reproduces precisely the full spectrum.
Okay, but what is obstacle for specialization to Q to I?
So there's no obstacle, but I think, so general Q knows, at Q is I, so general Q knows a lot about Q is I, but at Q is I more can happen, right? It's a very special point. So it does not know everything that happens at Q is I. So certainly we can, so actually, this example, I was cheating a little bit because secretly I already knew this happens for any Q, this descendant here. But if you go for higher to higher system size, and my picture becomes too, I can't quite draw it anymore, you get extra degeneracies on, well, we believe that you should get extra degeneracies on top of what we get by specialization. And that part I mean, it would be much nicer. So actually not just to have this Youngian of GL1/1 or whatever it's going to be.
Did you try to take divided powers for quantum loop generators?
Right. So this is what one should do, but unfortunately, I mean, so clearly that's what we have to do, but it's not so, I mean, the generators are not trivial, so it's not quite obvious to do this. But indeed, that would be the construction to try. And then there might be more on top of that, because at the free fermion points, there are lots of accidents, kind of accidental geometries.
Hey, yeah, so is the Hamiltonian for even n, is this nilpotent? And did you check the Jordan block spectrum? Did you see any interesting patterns?
Right, so for even length, so the eigenvalues, if you look at the eigenvalues, which we know for any Q, you can specialize them and they remain finite and everything is good. But if you look at the Hamiltonians, then certain matrix entries diverge of the Hamiltonian. So there are two things that one could try to do. One is chuck the Hamiltonian, keep the spectrum, and just try to kind of engineer another Hamiltonian which reproduces this spectrum. This would be an interesting question, and we do not know how to do this. The other approach that you can do is you can regularize the divergences in the Hamiltonian. By doing so, you kill the full spectrum, so you have eigenvalue 0 only. And then we have lots of Jordan blocks. So there we've done some numerics. We know that the Jordan blocks generally, like we get big Jordan blocks, again related to, I think, the presence of some sort of affine symmetry in general. So we know that we have Jordan's blocks up to system size, which I think is unusual compared to, let's say, XXZ with quantum group symmetry at root of unity. So we do have lots of extra symmetry there. We do not know quite we have not quite been able yet to kind of predict which Jordan blocks appear, how often and so on, but I think it should be doable.
Okay, thank you.
Any more questions? Anyone? No? Everyone's hungry?
Okay, yes, let's enjoy lunch.
That's